Good morning. So please welcome to one more session of reverse engineering. And if you are new to the channel, please like, share, and subscribe our channel. And this is regarding the operational amplifiers class that we have started. So as far as the operational amplifier is concerned, so how does basically an operational amplifier looks and what are its features? Let's start. Operational amplifier, as the name suggests, this exists as a chip. Okay, and it's basically a monolithic chip. Monolithic chip means, as the name suggests, it is made upon a single chip. Hence, the monolithic chip, the name of the operational amplifier. And the popular IC which utilizes this in the market is IC741. So basically, the operational amplifier, when we start the operational amplifier, so what exactly it is? We have input, we have an output, okay, and we have an amplification process. This is voltage amplifier, and we have this as your operational amplifier. So now, if you clearly look at this operational amplifier, the opamp, so it is essentially a voltage source. Voltage source. Okay, you can say it is a voltage controlled voltage source. So it is a voltage controlled voltage source. So there are certain items that are current controlled also. So here the gain AV is the output by V naught by Vi. So the elementary basic module of the operational amplifier, the previous class also we have seen, was like this. This is our supply voltage. Okay. Then we have a resistance. Okay. This is the resistance on the supply side, and we have the input resistance. So this is the input resistance. Then we move on further, we get this gain plus minus, this is AB into VI. So this is basically VI is the voltage in the input side, that is VI. And what else we have? We have a source resistance over here, and we have a load resistance. Finally we have a this is our this is our source. Here we will have output resistance. There is our resistance, and the power across this particular point will represent our output power. So there are some essential conditions we need to remember in an ideal circuit for such value. For ideal op amp you remember, apart from the R0, that is your output resistance, apart from this resistance R0, rest all, see, you have term R1. Okay, so this is equal to 0, your sorry infinite. Apart from R0, rest all values are equal to 0. So remember this. So this R0 is also your this voltage gain. Okay, V naught by V. This is also equal to infinity. Your for the ideal bandwidth also infinite, and gain into bandwidth, that is AV into bandwidth, is also equal to infinite. This is for the ideal case. So see what happens is that the AV, that is your gain, is given as infinity, and to get AV as infinity, what we do is multi-staging operation is incorporated. So multi-staging means operation are connected in cascade. So this process is called as multi-staging. So bandwidth, how do you define the bandwidth? So what is actually the bandwidth? So when I say a bandwidth, I have to define a bandwidth. So bandwidth would be a region wherein despite the change of the frequency, suppose I have uh, this point, okay, from here to here. So this is my lower frequency, this is my upper frequency. So this point, between these points here, you can see these points, even if I'm increasing the frequency, the width of this point, the magnitude of this point is not changing. So this point is would be the bandwidth point. So this is basically where when there is no change in the frequency. Okay, So this is actually the bandwidth. So we can say bandwidth is defined as the frequency range for which gain is independent of frequency. So bandwidth is defined as frequency range for which gain is independent of frequency. So this is one thing, gain is independent of frequency. Nice. So now the most important concept in any examination related to this is you will get virtual ground. To understand the concept of virtual ground, let's first understand certain characteristics, and before we move on to that, so gain in usually the practical op-amp, the gain of a practical op-amp is 10 power 6. Gain of practical op-amp, P means practical op-amp is, and op-amp is a multi-stage amplifier, you should know that, and ideally gain bandwidth is equal to infinite. So how do we go about it? For practical op-amp, gain into bandwidth would be equal to gain into bandwidth is equal to 10 power 6 hertz, and normally the gain value would be equal to 1. This is the maximum possible bandwidth. Okay, uh, so maximum possible bandwidth you get 10 power 6 hertz, and at that time the gain value is 1. So you have heard about these things, negative feedback, positive feedback. So why do we apply these feedbacks in a network? So why we are going for feedback and other things? So what is the reason? So basically what happens is that when we apply negative feedback, what happens is that it will lead to decrease of gain of the system. So the moment the gain goes down, what happens? It leads to increase in bandwidth. So if your gain goes down, your bandwidth increases. Okay, this is for negative feedback. So remember, this is for negative feedback. So what happens to the stability of the system? The stability of the system increases. This increases the stability. Now, what do you mean by stability? Increases the stability. Stability of the system means that it is in control system terms. If you say stability means a system is stable system and it does not falter. It remains within upper and lower limits. Okay, it does not rise exponentially. Suppose we need a range of a system, it should lie between this particular point 10 and 15. So if our graph is like this is to somewhat, it might be a stable, but if it is rising exponentially like this is an unstable system. We don't know where it's going to stop. So actually, stability and transients means if we have a DC sign or a AC signal, and we know that it is varying with some frequency of 50 hertz. Now what happens is that if it is an unstable system, so we don't know, there are some spikes, some trapezoidal, some like this, like that. Okay, sometimes it remains in the positive half cycle for a long time. Then there is no periodicity in it, and there is no particular order. So that system, you cannot design a system which is really unstable, but you have to think about it. So in and the method that is used for the design of this op-amp is Epitaxial method. So this method is called as epitaxial method. Epitaxial method is employed to design. So what is basically this? So in this method, what happens is the entire IC is fabricated on a single crystal. Entire IC is fabricated on a single crystal of silicon. On single crystal of silicon. So this is one thing. Okay, so one more thing, one important thing over here. These are some important points related to it, and already I have told you this voltage control device. Okay, so normal operation is IC747, and see where it is used. Like, see what it's a very versatile, predictable, and economic system. So it is used like for, see why it is used, because it has very high reliability and it's very cheap also. Moreover, it has offset voltage and current. Okay, low offset and low power consumption. Okay, so it was basically invented originally for the mathematical operations. Okay, that's the reason why it was called as operational amplifier. So basically it's a direct coupled, okay, it's not indirectly coupled high gain amplifier. Okay, and the open loop gain of this particular amplifier is very high, therefore frequency stability of the signal is less. And so now let's move to the main part, so where we will be understanding. So essentially if you look at the op-amp, so you will represent this op-amp with this particular signal. So if we are looking at op-amp, and let me use a background. Okay, this will do. That's good. Yeah. So if you are basically looking at an op-amp, so okay. So if you are looking at an op-amp, so basically essentially it, sorry, it looks like this. This is your op-amp. Okay, this is your minus, this is your plus. Okay, this is your V naught, and this is your VSAT, and this is your minus VSAT. And this plus terminal is the non-inverting terminal of op-amp. Non-inverting terminal, and this particular terminal is the inverting terminal, is the inverting terminal. So we saw that we have two terminals, one is the non-inverting terminal as an inverting terminal. So here the phase is equal to 0 degree, the phase shift here, the phase shift will be equal to 180 degrees. So what happens is essentially, suppose I consider there is a voltage, this voltage I take as let's suppose this be V1, and let this be V2. So and let this be the input voltage Vi. So the input voltage Vi will be, if I'm seeing from this point A and B, so if I say that VAB is nothing but as Vi, so what does VAB signify? It signifies VA minus VB. So what is my VA point? My VA point is nothing but equal to V1. What is my VB point? VB point is equal to V2. So how can I write VA? VA I can write V1 minus V2. Now this is one thing. Okay, now tell me, in there can be cases. Okay, if suppose there is a case wherein different cases I can encounter. Okay, so case I write that I know that Vi is equal to V1 minus V2, and the value of V naught by Vi is my gain. Okay, that is AB. In other terms, I can write V naught is equal to AB into Vi. So this is the thing. So I can write AB instead of Vi, I can write V1 minus V2. So now you people tell me please carefully, if you are analyzing this circuit. So how can I write? Okay. So if suppose, or now we have V naught. See, in a practical amplifier, what I stated is that I told you that in the very beginning I told you AV is equal to infinite. So AV to be infinite, suppose for AV to be infinite, what is the condition for AV to be infinite? See, AV is basically what? V naught by Vi is equal to AV. So, or what we can write? Tell me please. By now you must be able to tell me. So yeah. So V naught by Vi is equal to AB. Now you tell me, can't we write Vi is equal to V naught by AB? Yes, we can write. Now, if AB is infinite and V naught is finite, there is some value in there. So in that scenario, the value of Vi, what will be Vi equal to? Vi would be equal to 0, this Vi. So what is Vi essentially? Vi is equal to V1 minus V2. So we can write Vi is equal to V1 minus V2. So now 0 is equal to V1 minus V2. In that scenario, we can write V1 is equal to V2. So but these are two different points. So this point is v1 and this point is v2. Okay, so ideally how it is possible that both the points are equal? So uh, see, what one more thing that comes to our mind is, I have told you in the very beginning when I am drawing the normal circuit. So Ri for an ideal op-amp, instead of R naught everything is infinite ideally. So hence they should be open circuit. So the normal scenario will look like they should be open circuit. So if Ri is infinite, your Vi suppose is equal to I into Ri. So I is basically Vi divided by Ri. So in that scenario, it should be equal to 0. So I is equal to 0. That means open circuit condition. If that is the open circuit, hence they should be open circuit. But here when I am writing V1 is equal to V2, so that means these 2 points, when it is possible V1 is equal to V2, this is only possible if this is short circuited. So this is short circuited if they are having same potential. So this is only possible when 2 points are having same voltage, but they are different points. So this is ideally possible. So what happens is this in here is that um, this condition wherein we are seeing that for an ideal op-amp, both the potentials are at same potential. This condition is called as a virtual short, and even though they are not physically connected, they are behaving as a short circuit. So this is essentially, so what happens is that now this condition here we know that VA and VB are at same potential for an ideal op-amp. So but there is some certain conditions for this to happen. Okay, so what is the condition? Can op-amp for any op-amp this condition is possible, or for a particular case only this condition is possible? So if you see uh, this case of op-amp is possible for a particular case, and that particular case would be ideally when the op-amp is connected with negative feedback. So only in those conditions this is possible. So now later on when we are going to the session, I'll be explaining you in more detail. Now we have an open loop gain. The open loop gain is that if we have ideally like this vi and v not are connected, this is my open loop gain in between. This is my V naught and this is my Vn. So my open loop gain is represented by V naught by Vn. So this is my open loop gain. So I can write it AV or EOL open loop gain. Now coming to the closed loop gain. Suppose what I am doing is that in this condition, the same op amp, I have a different condition. So for the same op amp, what I do is I have my Vs like this. Okay, and Vs is my supply voltage, and I am connecting to my supply voltage again V naught. Okay, now this is my Vi connecting an AV to it, and I am connecting again V naught over here. So in this condition, if you see at this particular point V naught, how do you represent? If I write this multiplied, this is I. Okay, so if I have to take this as plus, okay, so this is Vs plus V naught would be equal to Vs. Okay, plus, okay, let this be plus minus. Okay, plus minus b into v naught into vb. So what, how I wrote this? So this is v naught. So how do I come to v naught? I come through this first vs. Okay, here it is. Again let me draw it for a clear understanding. It's a little bit confusing for some of you. Suppose this is plus minus multiplied. Okay, this is my vs point, and I have my current over there. I have my, this is B naught. This B naught is nothing but as gain. Then I have my VB point here, and I have V naught point over here. So I have tried V naught. V naught is basically Vs, okay, plus minus, okay, multiplied by gain V naught, and then this gain is getting multiplied to AB, and we are getting finally V naught here. Here we are getting V naught, okay. So we are getting V naught, okay. So this will get multiplied to PV, okay. So this is how we are getting. So now in order to get another thing is there, if you clearly notice this, here also on the top, if you see, that one more thing, that AV is equal to V naught by VI, that is nothing but equal to V naught by VS. In other terms, you can write VS is equal to VI. So if you substitute this, you will get open loop, this closed loop gain in terms of V naught by Vs, that if you solve the equation, you will get it around AV 1 minus B, AV, which this particular gain is less than the AB value, because in the denominator we are seeing less than the open loop gain. Why? Closed loop gain for this is for this case would be for positive feedback. Hmm? Positive feedback. Positive feedback means here plus value you will take. Now for the negative feedback, what is again for the negative feedback? If you closely notice, instead of V naught by Vs, instead of minus, AB would be equal to 1 minus 1 plus BAB. So you notice that this gain that you are getting is lesser compared to the open loop gain, that is AOL, in the closed loop gain for negative feedback. What is the maximum value of the gain? It is 1 for negative feedback. So we notice that closed loop gain, okay, is greater than AOL open loop gain for opamp with positive feedback, that is for opamp with positive feedback. But what about the negative feedback? In this case it is vice versa. For negative feedback we have negative feedback closed loop gain, this is ACL, is less than AOL. And one more important concept, this virtual ground principle is only applicable, virtual ground principle is applicable for negative feedback. Remember that, not for applicable for negative feedback. Now, one very important thing is that all the other devices apart from the oscillators are negative feedback, have negative feedback. Only oscillators are having, for only oscillators have positive feedback. So we will conclude this session with one gate problem. Recently it has appeared, and let's analyze the concept what we have learned, and let's solve this problem. Okay. So the basic things you require is basic electrical engineering knowledge and the concept of virtual ground. So this is the problem that has appeared in 4 point. This has appeared recently in 2015 gate examination. So the question is like this. So I'll write the question. Consider the circuit shown. R is equal to 1 kilo ohm and C is equal to 1 microfarad. The input voltage is 50 hertz, represented as Vi at an angle 0 degree radian. Okay, so you have to be careful. The output voltage is represented output voltage V naught at an angle 0 degree, and phase angle phase angle is this delta radian. So what is the value of the output phase angle? So what is the value of output phase angle relative to the input phase angle of the input voltage? So this is the question, how we are going to do this. Essentially, you see, I'm going to draw this. This is a capacitor, and we have one more capacitor down here, and we have two capacitors that are connected to opamp circuit. We are connected to, sorry, some problem here. No problem. Okay, so we have two capacitors. So one more is here. Okay. So and this is connected with the resistance. This is R, this is C, this is C. This is V0 is equal to V0 at an angle of alpha, and Vi here is equal to Vi at an angle of 0 degree. So this is Vi. Vi is the voltage across these 2 points. So for the time being, yeah, so no problem. So this is the problem. So this is all what we have. Okay. So and there is one more resistance. Sorry, there is one more resistance that is going down, and this is being grounded. Essentially, in op-amp circuit, we know this is a virtual ground concept, so we have to solve this problem and we have to get to the angle. So how do we go about this problem? So if we carefully notice, if I say my current I is entering this point, okay, A and B, and now I know that the potential at this point and this point is same. This is only potential same, 1 I into R would be same. So R is not same. So that means for potential to be same, this current has to be go to this point also and has to remain same. So if I name this current, whatever current that is entering this op-amp circuit A from here will leave also from here. This current will be the same current. Now if I see the circuit VAB, so in the loop VAB, I say that VA is equal to VB. Okay, now can I go for the virtual ground concept? First of all, let me write here VAB. So if I say this is my plus point, this is my minus point, okay, and voltage source is connected like this, and this is my plus, this is my minus, and the direction of the current is like this. The direction of the current is like this. So like this means it's going like this. So across A and B, across this point, it is going in the direction of fall across this capacitor, and across this voltage source, it is going in the direction of rise. Again, across this capacitor is going in the direction of fall. So I can write V rise is equal to V I at an angle 0 degree, and V fall is equal to I into 1 by SC plus I into 1 by SC. So I can write V rise is equal to V fall. V rise is equal to V fall. So this V rise is equal to V fall would lead me to I is equal to Vi SC by 2 if I solve this. Now if I see my V over here, see the current direction is reverse. Okay, current basically the direction which we have chosen here is plus minus. but the current is going reverse, so it will be minus I into R. So VA I can write minus SCR VI by 2. I substitute the value of I over there. Similarly, VA is equal to VB, that is minus SCR VI by 2. Now, if I see the upper circuit, VB minus V naught here, this upper circuit I can write VB minus V naught divided by R, nothing but at I. So, in other terms, I can write V naught is equal to VB minus IR, and I get the value V naught, substitute all the values back, minus VI SCR by 2, for I also I substitute VI SCR by 2. So minus minus will become how, and 2, so it will become V naught. V naught will be equal to minus VI SCR. So one thing I am noticing is that minus sign is there, and S value if I put by j omega, so I get V naught is equal to minus instead of S j omega R CVI. So what I notice is that V naught lags VI by 90 degree. Okay. So in this particular problem, this 4 point, so I can clearly see that V naught lags VI by 90 degrees. So the phase shift is minus 5 by 2 radians. To get more video lectures like this, please subscribe to our channel and support us. Thank you very much. We are winding up this.